to tell me later it was wrong. And I was like, ma'am, is it right or wrong?
Alright, we're going to start going over these. I know we may not be completely done with 1.3. Hopefully you are. Have 116 out so that you can take notes as we go over the different pieces of that formula. Hopefully we recognize some of those pieces of the formula. Alright, so what career most interests you? Welding, carpentry. Alright, cosmetology, don't know. I like art. Probably can't make a living off of it. You'd be surprised. You could work at museums or art galleries, things like that. Medical, orthodontistry, still figuring it out. Teaching, interesting.
No.
You know what I never wanted to be as a high school student, or even more than halfway through college? Never wanted to be a teacher.
I just don't make it up. I'm sorry, I can't
I
I don't like
mean,
kids that much.
it depends. One, they've done some pay raises. Like a starting teacher with a bachelor's today makes $40K, which is not bad. And then if you get a master's, you start at 45 or so. By the time I was teaching for 3 years, I was making 50 because I had a master's. So like you can do okay as a teacher, and if you ever go into math or science, they have special teams contracts that depending on how many years you've been teaching, you can get more. Yeah, this is the first time I've ever felt like I've been paid adequately as a teacher because of that team's contract, but I'm actually paid pretty decent, which is yeah, why?
Because like a nurse with a social degree makes more than that, and y'all have a bachelor's degree.
I feel like
A
y'all
nurse
should
with
make,
what?
A social degree.
It depends, because I have some friends who are nurses who have bachelors and even are RNs at this point. They don't make a lot more than me. Plus, the benefits of being a teacher, for instance, like retirement is really good. And what was the other thing? Healthcare is stupid cheap. Like healthcare for me is $30 a month. It's more expensive for my wife because it's not subsidized as much, but healthcare is super cheap compared to other things. Basically what I'm saying is I wouldn't discourage anyone from being a teacher. I know a lot of teachers who do, and I don't like that at all. The first one is periodic, the implication being that the second one is what?
constant.
There was another C word we used.
Continuous.
Continuous, right? There's periodic and then there's continuous. One uses Euler's number. Which one uses Euler's number? The second one, right? That continuous formula is the one that is using Euler's number, because when we start compounding continuously, what does that start to approach? 2.718. And really there was more decimals after that, but that's that Euler's number, the number E. So I'm glad to see that we are recognizing the periodic versus the continuous there. Then we have this last question. So this is important. What does the T stand for, right? We are looking at this formula, n of t, making my independent variable what? Remember, the independent variable is inside the parentheses, because notice how it's inside parentheses, so that's what you would substitute n for. That's an input or an independent variable. So n of t equals n sub 0 times e raised to the rt. That's the formula we're looking at. We want to recognize that t is time, and that is important. There was something else I was going to say with that. Yes, ma'am?
Is E standing for the, like that weird number that we remember?
I think it's the next one.
And I was wondering if that's the,
So
number, then what do they do since it's continuous? Like, can they only put in 2.718, or do they have to put like a whole?
So just like pi, what do you put for pi?
A little symbol?
Little symbol, right? Or 3.14. So remember, E is approximately 2.718. Just like pi, we approximate it to 3.14. So if you're writing out by hand, maybe you put 2.718, but wouldn't it be much easier to just write the number E there? So we use that. And where can we find E on our calculators?
In the pi side?
Right, so if you hit the pi symbol, it gives you that option for E. But yeah, 2.718, remember that's approximate, and we call it Euler's number, or the, it's up there, or the natural base. So initial value, we do want to recognize, this right here is known as just the initial value. Just like when we had a of t is equal to a times 1 plus r divided by k raised to the kt. That first number was the initial value. Or you could also think about it as your y-intercept, right? That is another important way to think about it, is that's our y-intercept. Does anyone know how we read that value? There's two different ways.
What is the end of difference stand for?
Well, for some reason, and they don't always do this, our textbook is using n to represent the value. That's not always the same symbol. I've seen a of t here and a sub 0, they're using n to differentiate the continuous versus the periodic.
So do we just say the value of, like, what you start out with, or like? what-
Well, so you could say initial value,
Okay.
right? Just like we would say a right here is the initial value. By the way, there is a chart on in your book. I would probably make notes of these things, because any kind of assessment, I am going to give you the formula. You just have to be able to substitute those values in, so you need to know what the formulas are. And this is on M3-116. Okay? So that's the initial value, but just because I'll say this, does anyone know how we read that expression? There's two different ways.
Sub-zero.
You would literally say n sub 0, because what is the initial time? 0, right? So that's why it's n sub 0. And I don't know as much why the other one is said this way. I'm sure it's from some other language or something I'm just not aware of. But you would read it as n naught. I don't even know how to spell that now that I think about it, so I'm not going to spell it. But n naught is how you would read it, which I guess naught being nothing, or the initial time is nothing.
N-O-T?
No, I think,
Or is it like not T, like N-A-U-G-H-T or something weird? Like, have you ever seen how they spell
how
Dotson?
to read.
Isn't that like a German one or something?
I'll have to look it up while y'all are working on stuff later, but I'll have to look up exactly how we're supposed to read it. But it's in naught, I know that, or how we spell it, sorry.
It's like K-N-O-T, like a not.
See, naught, that kind of naught is how fast a ship is going, so I don't think that, I think it's N-A-U-G-H-T.
That's what I said.
I did not hear you say that, that's my bad. What does R stand for? The one thing I'm going to say is rate is the better answer here, because does it have to be dealing with money? No. Interest rate implies it's dealing with money. We don't know for sure it's dealing with money, but we know it is the rate that something is changing. Does anyone remember other places we might use this formula other than banking? I mentioned this last week.
Population.
Populations, right? Populations are continuously growing or decaying. I mentioned another option last week. Dinosaurs.
Oh, there's that how long.
That C word is carbon dating.
Yeah.
So we know how quickly carbon or other radioactive materials decay, and because we know how often those things decay, we're able to use that continuous compounding formula to figure stuff like that out. All right, so that was a good solid 15 minutes review. Any questions before we get started with today? Yes, sir.
What is NT?
Yeah.
Oh, that's a good question. So, was that in here? It wasn't. So, it was one of the questions?
It's in the chart.
Well, we got
It's-
T.
It's in the chart, yeah.
That's why.
Well, so like if n naught is our initial value, right? T is our independent variable. So this is the value at t time, right? So this would just be our value at time t, or depending on time t, right? N is our dependent variable, and so it's the value depending on what time it is.
By the way, I wasn't saying you don't make enough, I'm saying for your job, like for what you have to do.
Oh, yeah.
Like this class alone, you're basically babysitting like a full thing plus teaching us stuff for like a long amount of time.
That's fair.
So.
And I know what you're saying. I was saying that I don't want people to just hear that, because I want people to be encouraged to go into education, because I've actually heard teachers discourage people from going into education, and I don't like that.
Yeah,
Because-
every teacher I've had has been like, don't do it. Just
Yeah, I think education is super fulfilling. Is it tough? Yes, especially depending on what class it is. Like, I've had some classes that made me question everything, but overall it's worth it. So we're gonna finish up PERT and NERT, the exponential functions, before we get into module 3, topic 2, lesson 3, which is all about the inverse of exponential functions. So I'll get you there. So we filled out this chart already. Why is E used as the base? Because
it increases.
so it's not just that it keeps changing, because remember the periodic compounding formula kept changing as well. Like it kept changing over time. Where did we get that E from? Think about the name of this formula.
That person.
Well, we didn't name it after Euler, but how did Euler find this number? How did we find this number? Because we were doing what with the compounding? It was continuous. We use E when it is a continuous compounding scenario. Right, it's continuously compounding rather than periodically. Okay. Whoa. So, how, anybody have a guess as to how we could use this formula to represent a decline in population? Negative what?
Yeah.
A negative E, so it would become n of t is equal to n sub 0 times a negative E
Yeah.
raised to the RT. But if it's a negative base, right? If I have an odd exponent, it's going to be n sub 0 times like a negative E. But if it's the t is 2, right, 2 years later, that'd be n sub 0 times a positive E squared, right? Can you have a negative population? No. Come on, a negative is right. Well, even then it'd be 0, not a negative. We do need a negative, but what is negative? Looking at the different pieces, if the population is decreasing. R, the rate would be negative. And so that's what we want to recognize here. And so what we just say is to decline, and I'm not going to put a negative in, but to decline R, how would I write this algebraically to show it's negative?
The negative sign.
No. How would I write an algebraic expression or equation or inequality to represent its negative?
Can't you put a little line in front of it? You know?
Think about what I said again. Well, so here's the issue. If I put a negative in front, that's a good idea. But if I put a negative in front and R is equal to a negative 2, then I get negative times negative 2.
Oh, so.
So what would I need to write?
Negative parentheses.
Yeah.
A negative and then a parentheses like this?
Well, we put the negative in the inside. Yeah, put the negative R and then put the parentheses around the negative R. Like I said.
Same issue though. Even if I have negative R, if R is negative 2, then it's negative times negative 2. Listen to the question again, because we already did this once. How would I write an expression, equation, or inequality to represent that R is negative?
Oh yeah, could you do, like DJ said, like it times negative 1 or times.
R is less.
0.
Thank
Yeah.
you. We've done that, haven't we?
Where does T get though? Where's T go?
Well, the T is still positive, but I'm just saying if the population is going to decline, the rate is negative, the rate is less than 0.
R is less than 0 times T.
Well, just R is less than 0.
But I was asking like, how do you keep doing the equation if you don't?
Because everything else would stay the same. I'm just saying that to have a declining population, R is less than 0. That's all I'm saying. The T is still 1 year or 2 years or 1.7 years. And also think about it. Remember, can time be negative? Nope. So what's a negative times a positive? Negative, right? So the time is still time. You're not changing the time. And I'm not changing the R either. I'm just saying if the population is declining, the R has to be less than 0. Alright? So like if I were to say the population decreases by 0.2% per year. Actually, just say 2% to make life easy. 2% per year, R would be a negative 0.02. Not a positive 0.02, a negative 0.02. Does that make sense? That's all I'm saying there.
Does anybody have 0.5 really? Sorry, I'll pause it. My pencil's not working.
Yeah.
Anybody?
Alright.
No.
Any questions about that? So please understand, you would still plug, if I were to tell you T is 3 years, T is still 3 years. If n sub 0 is 500, it's still 500. E is E. We're just saying that if it's declining, the R has to be a negative number. That's it. Okay? Okay, so we're going to actually jump back a little bit to understand where we're about to go. This is M3-7, and you need to pay attention to this opening part of this lesson because it is fundamental to everything we're about to do for the next week. M3-7, yes ma'am. Okay? So, one of the things that we have studied pretty heavily is the idea of functions. And now what we're going to look at is called the inverse of a function. We have talked about inverses in the past. In what context? Not just numbers.
Fractions?
It did deal with fractions.
The inverse, the
Reciprocals are multiplicative inverses. What would I do to solve this equation? I would add 4. What is the relationship between adding 4 and that minus 4? They are what? Inverses, meaning that they are undoing each other, right? So, we have studied inverses, but I want you to notice, is this an inverse function?
What page are you?
M3-7? It should be. It's It's backwards. M3-7.
Oh, I was right.
Got it.
Are we there now? We good? Okay. So, I want you to notice this question. This is important. Is this an inverse function? What I did here. We have the inputs and outputs. No, so it's not a function. This would be an inverse what? Well, we have an equation. We use the properties of equality, but this is a mathematical what? Starts with an O. Say it again. Cameron?
Operation.
Operation. Right? Adding, subtracting, multiplying, dividing, square roots, squares, all those things are mathematical operations. And we've done a lot, and you've done a lot throughout your entire high school math career, and even in middle school, with inverse operations to solve equations. What we're going to talk about today is not just the inverse operation, but what is the inverse function? Right? There are things that undo operations in an equation, and they are heavily connected to what are inverse functions. However, there's a fundamental part that we should have covered in previous math classes and probably didn't get there, so we're going to talk through it here. And I'm going to let y'all work within small groups soon, but we're going to have to go through this together. All right, and we're not gonna do the whole patty paper deal. We're gonna talk about how we could show a reflection of the polygon across the line y equals x. How would we reflect this polygon across the line y equals x? Notice that's already there. It's a mirror, right? So where do you think this point E would end up?
Yeah, positive.
So opposite point right across from it?
Yeah.
Right here?
Yeah.
Or here?
No, down at the.
Why here instead of like here?
You just flip flop.
You're flipping.
Yeah. I thought it would be down. If you flip it under big three.
You thought it'd be like here?
No, she's talking about flipping it upside down
Here?
and then flipping it like an inverse.
Come here, show me.
Yeah, yeah,
It's
yeah,
okay.
that, the
What do you think it is?
reflection thing.
It is called a reflection. Show me what you think it is. Come put it up there. Show me. I can't figure out what you're saying. It's okay. Come on.
Yeah, I was thinking the same thing.
I don't know.
Yeah, yeah, you're good. Show me. You think it's down there?
Yeah.
So maybe like here? Don't know?
I don't like
Okay.
reflections.
Well, so let's define something important. When you reflect, how do you reflect in respect to the line that you're reflecting over?
I thought you just.
I thought you kept it on the
But you-
same points, just the opposite, if that makes sense. Like that one's on 4, 1, it's on the other side, it'd be on -4, -1.
So,
In
okay.
the opposite,
So,
mathematically.
really quickly, I need you to hear me on this. Typically, you're used to reflections being across the x and y axis, which is why we're used to just the sign becoming a negative for one of them, right? But I need you to pay attention to this here. That's an incomplete understanding of reflections. This is going to matter for the future. When you reflect, you always reflect perpendicularly. So for those of y'all who are thinking it's going to be somewhere in this region, see how that line is perpendicular to my line of reflection. And it is important to notice that this line right here,
What is perpendicular mean?
at a right angle, okay?
Oh, okay.
Perpendicular lines form a right angle. It's also important to note that their slopes are opposite and reciprocals. I'm not going to go into that right now. So that's the first part of reflections. It has to be perpendicular to whatever the line of reflection is. And then how far do you go to the other side of the line of reflection? Yes. So you reflect perpendicularly and maintain distance to line of reflection. So, knowing that, and knowing that Lexi originally said right here, correct? Does anybody want to push back on that point after the reflection? Nobody wants to push back on it? Say again? This is just a definition for reflection, yep. What'd you ask? Okay. It's got to be perpendicular, and it's got to be maintaining the distance to the line of reflection. Does anybody have a question about that? No one's disagreeing up to this point. Anybody have a question? Okay, do you see this distance, how far it is? It's like half a block to this line of reflection. So how far am I going to go to the other side? Half a block. And then that line is perpendicular. Notice how this line here has a slope of 1. So my perpendicular line has a slope of -1. Okay? So I just have to go through that line, creating a perpendicular line there.
Was that right?
Yep. You act like you don't ever get anything right. So where would this point go? This point G, that's on the line of reflection.
Right there. There.
How far would this point be from that line of reflection?
2, 3, 4. 4.
How far would that be away? Like 1 block, right? How far is this point from the line of reflection?
I thought it would stay the same for the Oh, yeah.
Okay, raise your hand if you think it's going to stay the same place. DJ, Lexi, Gracie, Grayson, what about you, buddy? You think it would stay in the same place? Yeah? Disagreeing to agree?
Yeah, I just thought it stayed on that point and then like,
Okay, why would it stay on that point?
it's the middle.
That's on the line.
It's on the line, so how far is it from the line? 0, so is it going to move? No, it has to maintain a distance of 0. So it's going to stay right there. Alright? So where would F go? Tell me coordinates. Looking up here, where do you think it would go? Or looking at your sheet as well. Where would F go?
4
So
down.
5, comma 1. Right there.
1, 2, yeah,
Oh, yeah.
4 down.
Notice is that line perpendicular? Yeah? And then visually, we're just going, there's 2 blocks, the diagonal of 2 blocks, so we got the diagonal of 2 more blocks. Okay? So we've got part of this now. Go ahead and fill this in. Alright? So point D, talk within your groups, 30 seconds. Figure out where point D is going to get to. Talk within your groups.
You want us to get it to another letter?
Well, not to another letter. I just want to know where is that point going to end up. Find the coordinates for where that point would end up after a reflection.
You just flip it. So,
I'm just trying to imagine where it is. Like if this was here, like, like flipping.
Coordinate, is that 2? Switching your negatives and positives.
for D,
So 2,
4, maybe 2.
Alright, let's bring it back in. Kyla, what did your group come up with as where this point would go? Say again? Yeah, talking about point D, where did that point go, do you think? Or did your group decide?
Like over there by 5?
So over here?
Yeah, somewhere over here.
Somewhere in that region? Okay. So could it be this point? Whoops. Why not? Can anyone visually tell why not? It's not straight across, meaning the line is not what? Perpendicular, okay. Maybe in that region though, does anyone have an option that they think might be accurate? Gracie?
3, negative 1,
3
and then get out 1.
and negative 1 here. Okay, so is that perpendicular?
Is there more than 1 point?
There's only one point that it can be. But I mean,
That's just
first
the
question, is it reflected perpendicularly?
Yes.
Look at that angle, right? That's actually a right angle. Notice the slope was 1, now its slope is negative 1 of this line. Is that maintaining the correct distance to the other side? No? So DJ, you say no, so where do you think it would be?
I think it's 4, like 4 negative 2.
Notice we have 3 diagonals here, 3 more diagonals there. So 4, negative 2. Excuse me. Thank you.
I just drew it out based on where the line goes in the boxes. Like if you start at the point and you only take like a little corner of it like they did, and then almost half, and then over half, and then there. That's
So you like down, but you go down 1, 2, 3 to the right 1, 2, 3. So you need to go down 1, 2, 3 to the right 1, 2, 3. Does that make sense, to maintain that distance? But what I looked at was the diagonals, right? 1 diagonal, 2 diagonals, 3 diagonals. So how many do I need to the other side? 1, 2, 3. Does that make sense?
Yeah, I mean, not really, like, not when I drew it out, like,
But look at your point here. How many diagonals is that? 2. How many diagonals did we have here? Are those the same distances? So we have to make sure we maintain distance to the other side. Okay? Alright. So, LaShannon, could this be my next point? That point C? Could that end up there?
I don't even know, I don't know how to do this, I know how to
yeah, I'm
I
kind
don't
of
know.
now.
What do you know about a reflection?
do it reflects on itself, it looks the same on the opposite side, so.
LaShannon, you're not even remotely looking at the definition I just gave you.
Oh, well, yeah, it's perpendicular.
Okay? So let's think about it. Does that look like it is perpendicular to my line of reflection?
I mean, yes.
Is it forming, does it look like it might form a right angle?
You talking about to B, the point on B,
No.
or?
I'm trying to reflect point C right now.
Okay, if you're trying to make a triangle that looks the same as the top.
No, I mean, kind of. That's not, but I'm just talking about this single point. Like, once I get my points on there, then I just connect the points.
Well, yeah, it can reflect the lower you go though.
That's not the question I'm asking. Notice I created this teal line right here, correct? Is that line perpendicular to my line of reflection?
Yes.
Okay. That teal line is where my point C will end up, somewhere along there. It's going to be somewhere along here. It might be here, it might be here, might be here. And my question is, somewhere along that line is the correct point after I reflect it. Are any of these the correct point after I reflect?
No, I don't think so.
Why not?
Cause it don't make a triangle.
That's not what we need to be thinking about. Where in the definition of a reflection does it talk about a triangle?
It don't, but I'm saying how it looks. I don't understand.
Because you're not focusing on the definition. You're trying to talk about a triangle and there's no point of a triangle in the definition.
You're supposed to maintain distance,
Okay.
okay. I don't understand how far you want me to plot the point.
How far is this point from my line of reflection?
It's gonna be too off the line. It's gonna be like, let me see, it's gonna be.
This looks to be 2 diagonals.
1? It's gonna be negative 2, 1? Well, no, it's gonna be going, it's gonna be 1 negative 2, not negative
So this point is what you're thinking.
2. No,
Why not?
it's too, because it looks too far from the line.
Right.
So
That's-
it would be, 0, no.
Look, you have to be along this teal line, right?
It's gonna be 0. Negative 1.
Is that the same distance?
It looks like.
Notice it's only half a diagonal. So then on this side I need to go half a diagonal.
Is that right?
Yes.
Oh.
That's my point. You just have to go half a diagonal. Okay? So from here, we only have one more point left because notice that's going to stay on this line here. Okay, so Jaden, how far do I need to go to the other side of the line of reflection? Dude, you're trying to get out of trying to answer. look right here, how far do I have to go to the other side of the line of reflection? Were you paying attention when we were talking through this with LaShannon? So we just did it. I'm like, how are you gonna learn if you're not paying attention? How far to the other side of the line of reflection?
2.
Okay, so are you thinking like here? Because I think you're thinking about it correctly, but notice that's 2, because I'm starting in the middle, so 2 would end up in the middle over here. Can anybody help Jaden out? Gracie?
I think you would raise it up to the corner of that box and.
So like here,
The other point,
that point?
yeah. Because it has to go back down to get to the other point like that one did, from B to A. You
I
know,
would say that other point that you pointed at.
The original one?
No, yeah, that one. 'Cause
Oh,
that
yeah.
would be like a whole block and a half.
yeah, that looks fine.
Notice, Jaden, see how it's a block and a half diagonal? So half a block and then a block diagonal. And notice, Gracie, it has to be here because it has to be perpendicular.
Mhm.
We good with that? Yes? Okay. So that would be our final point. And so look at it overall now, without all these extra lines in there. Does that look like a reflection across y equals x? Okay. But notice, and LaShannon, I need you to pay attention because you're trying to get distracted by other things. This definition is what defines a reflection. You gotta be perpendicular to that line of reflection, and you have to maintain distance to the other side. Or maybe I should say that, to other side of line of reflection, okay? Now,
What is Patty?
don't worry about it, we're not focusing on it. Okay? Now, I'm going to point out a couple of things because this is going to help you understand inverses. This is not an inverse function because it's not a function, but I need you to notice this right here. This point F was the point 1, 5. What is this new point right here that came from F? 5, 1. G was originally 5, 5, and what did it stay? 5, 5. Alright. C was -1, 0. What is this new point here? I want you to talk within your groups. Take, let's say, 60 seconds. What is the rule? What is happening to the point every time we reflect across y equals x? Talk within your group, 60 seconds. What's happening to the point every time you reflect across the line y equals x? F originally was 1, 5, now it's 5, 1. Remember, just look at those coordinates. And guys, you should have this drawn in there so you can refer back to it in the future. Look at each of those points. Jelani, you awake there, buddy? Come on, talk to it, y'all. Switches input and just switch an input. Alright, that's our 60 seconds. Grayson. What's the rule y'all came up with? What's swapping? The x and y values are swapping? Did anybody say that a different way? Inputs and outputs. Okay. Anybody want to push back on that or do maybe a different idea that we were thinking about?
It's just swapping X and Y, that's all I can think of.
So if we're swapping x and y's, this point B was -5, comma, -2. If we swap x and y, what do we get?
Negative 2, comma,
Is that what this point is here?
it should be, yay. Awesome.
So is that a good statement? True statement? Yes, sir.
What is mine?
Camp, Hollander.
He's not in here. Okay. So compare the coordinates of the vertices of the original polygon with the coordinates you wrote in question 3, which we kind of just talked through this, but the x and y coordinates, or x and y values, that's not an and y, it does. Coordinates / values, which I really like what LaShannon said here. What's another way to say x and y coordinates? Inputs and outputs, right? And the one thing I will say is I'm going to say the word switched instead of the other one just because it's a little bit more mathematically accurate. So they switched. And I need you to hear me very clearly on this. This is what an inverse function does. An inverse function is a reflection across the line y equals x. So what's going to happen to every point from the original function to the inverse function? They switch. This is an important definition here. An inverse function, and we would explore this more heavily in, if we had more time, but as y'all always hear me say, we are always behind. So an inverse function is a reflection across y equals x.
I know why I messed it up. I thought the line in the middle was like finishing off the shape, if that makes sense. I thought all the points that were in the middle, like I started from that dot, the third one from the top or whatever, and then I just pulled the other thing to the other side without moving that dot over.
Gotcha.
Is
Okay.
there ever gonna be a shape that's like that, where it's like the middle is also, like the line through the middle is part of the shape?
No.
Mm.
You may draw it in there to make it look like it, but to help you visualize it, but even here, the line y equals x, well, I guess there was that part that was part of it. No, but no, that won't be there. Okay? So an inverse function is a reflection across y equals x. So this rule that we wrote for number 4 is followed for inverse functions. This is an important definition that will impact what we talk about in just a second.
So what if they use this?
Inverse functions. So all the inverse operations that you studied also work with inverse functions. Also, let's say that I have x squared minus 4 is equal to 12, right? Plus 4. So x squared is equal to 16. But what are you going to do at this point?
What squared equals 16?
What is that, equal something or no?
What squared equals 16, but also what's the inverse?
Oh, square root.
Square root. You can actually write inverse functions so that you can just plug stuff in without having to go through this multiple times and use a calculator or a graph to figure this out. So for example, the inverse of y equals x squared minus 4. Notice what was the first thing I did?
Y equals.
So y equals x plus 4. And then what was the last operation that I did? So y equals x squared minus 4, its inverse is y equals square root of x plus 4. Now, I can just graph things and find all those points really quickly if I need to find those inverses, multiple inverses, or multiple values. So inverse functions are applicable in a lot of situations. There's actually a unit that I helped develop with a professor of mine at UA that I really like to do with inverses, but guess what? We got all of a week and a half left. I'm gonna try to speed things up in the future so I can get there with future classes. Sorry guys.
Did you get back on the information for your grant?
I told y'all that last week.
You said you were going to the next week.
And all I see left is.
I never told you I was gonna tell you on the 6th. I told y'all last week that we got to a rule that, oh, they did have to talk to the board. I thought Ms. Mara told us. I don't know yet. I have to ask Ms. Mara
About what?
if we have exemptions or not.
Oh.
I would assume / hope. Okay, so this is M3-125. So we're jumping back to where we were. Please note M3-7 is where you need to go for definition of an inverse. But we're going to use this here because we've studied exponential functions very heavily. Any guess what the inverse of an exponential function is, or an exponential expression? A logarithmic function. How'd you guess that?
It says it.
Oh, it's a key term for the lesson, right? So, I'm not going to try to trick you or anything like that, but we do need to learn what a logarithm is. I'm sure some of us are looking at that word and like, Mr. Kinney, that's freaking me out because I've never heard that word before. Quit it. Every new term is going to be something new. It's not scary. It's actually very, very straightforward. And so we're going to learn about what a logarithm is. And so notice, it says here you've investigated inverses of linear, quadratic, and power functions. Unfortunately, we haven't done as much as we should because time. But we're going to try to identify some characteristics from the inverse of exponential functions known as logarithmic functions. So, consider the table and graph for the basic exponential function f of x equals 2 to the x. Notice, here's my base function, right? 2 to the x. Here's the inverse function. What do you immediately notice about those points? Be careful about the word opposite. What does the word opposite mean in math?
On the other side of the line, from 0.
Negative versus positive. So, kind of, but when we say opposite mathematically, we're only talking about if it's positive, it becomes negative, and if it's negative, it becomes positive. So what's really happening here? They're inverted, switched, right? Our x and y values are switched. But the term inverted is actually the most accurate word. Not something I was planning on bringing up, but I'm glad you said that, right? Because what is the name, what's the relationship between these types of functions? They are called inverses, right? They're inverted. The x and y values are switched. Now, I do want to point this notation out to you because many of us are going to be freaked out. F of x versus f negative 1 of x. This notation right here is not a negative exponent. It just indicates the inverse function. So I would make a note about that. This f to the negative 1 of x just indicates inverse function of f of x. That is all it is. Not taking a reciprocal, we're not dividing, we're not doing a negative exponent. That f to the negative 1 of x is indicating the inverse function. Okay? And so, graphically, right, we already see the x and y values are switched. Graphically, how do we know that this is the inverse function? Where did that inverse graph come from? Say again? No? It could come from the table, but y'all are abandoning what we just talked about.
F of x swapped.
Kind of. What is causing the x and y values to switch?
Oh, people who wrote the table.
No. Not a reciprocal.
Oh, the reflection.
The reflection of across what?
Woo,
The line.
Well, we use a perpendicular line, but what was the line that we were reflecting across? It was y equals x.
Yay.
Right? Notice here is the the graph of y equals x. I would graph this in here.
That took us a minute.
You don't have to do all those points, but I know it's new, so we're not quite used to it. But here's some points. right? That reflection, can you see it now where we have reflected across this line to get each of these points?
Yes.
Hopefully, right? So, inverse of f of x comes from reflection across y equals x. Do not forget that. That inverse function is a reflection across y equals x. And we needed a name for it. John Napier is the guy who, he didn't invent them, but he heavily worked with these things called logarithms, or that he dubbed logarithms. Okay? But let's look at this getting started part of this, because we're going to see something really important here. Complete the table, f of x. What is the domain of f of x, this 2 raised to the x?
Well, it's already done, ain't it? It's already sitting there. See that one, the upside.
What?
I don't know.
What's the domain of f of x?
Infinity something.
Negative.
Yo, what's domain?
I don't know, man.
It's the set of all inputs by x values. So I'm thinking left versus right. What is the lowest x value? Negative infinity. There's an arrow over here, so it's going to continue going to the right. So what's the maximum x value? Positive infinity.
The other one's flip flopping.
Like positive
You're gonna be
infinity.
positive and then negative.
Interval notation is always from a what to a what?
Well, I
No,
don't
no,
know.
no, no. We've done this too many
Usually it's
times.
X and
What's
Y,
always
now
the
it's Y
first?
and X.
No. What's the first all the time?
Just the lowest.
The minimum, comma the maximum. Remember, this isn't a point. This is an interval.
So you're
No, sir.
It's gonna be flip flop.
What? No, it's not. First off, can infinity? Hold up. Can infinity be the minimum?
It's
No.
gonna be the same thing.
No, it's not.
It's not.
Look at that graph. What is my lowest y value? No, it's not. We just dealt. Yes, because we're on range. We just did a lot with
We were
exponentials.
talking about the other one.
Oh, I never said that one. No.
We were, yeah.
I said, what is the range?
range?
Huh? 0, comma, infinity.
Yeah, we were talking about
Y'all, so I understand a little bit, but y'all need to look at that graph again. Because there's an important thing that we're not seeing yet, but you will in a second. Do you see how that arrow is approaching the y-axis?
So it's gonna eventually equal 0, right?
It's not going to equal, but it's going to approach. So I need you to look at that again. What is the domain for that inverse function?
Approaching 0.
It's approaching 0, so what's the lowest in the domain? 0 with a, well, I meant like parenthesis or bracket. Remember, it's approaching. Does it ever equal? No. Comma, what is the largest domain value? Infinity.
Yay!
Okay, what's my range?
We did it. That took so long.
Negative infinity, positive.
That's weird.
What's weird?
What's weird about that? It's inverted. Because what's happening to our x and y values? They're switching. There we go. Domain and range switched.
Now they're going like diagonally on things. Like look. Do an X. Do an X where you just wrote your things. You see what I'm saying?
Oh, she's talking about here versus here. It's more, and we want to pay attention to the fact that domain is my x, range, remember, is my y. So when we did the inverse, the domain and range switched. So what was my y-intercept of
One.
f of x?
1.
0, comma 1. So what is my y-intercept for the inverse of x?
1,0.
Would that be a y-intercept?
0, 0.
Look again, does it ever have a y-intercept?
It wouldn't
Well, it probably is gonna approach by itself.
But it's going to approach, but is it ever going to get to?
Oh, well, no, so it's not, it's not. It's
So
gonna
there
be
would
an error.
there would be no
No y-intercept. It's gonna approach the y-axis. Is it ever gonna get there? No, but I will say, I don't like that they did it this way. What I would say, and what y'all were picking up on very quickly, we would have the point 1 comma 0, but that's not a y-intercept, that's an x-intercept. So we'd have an x-intercept of 1 comma 0. Make sure you note that, right? That 0 comma 1 becomes 1 comma 0, because what are the x and y doing?
Switching.
They're switching. Okay? This was newer. But does anyone remember what the asymptote was for this exponential function there?
I forgot what that was.
Yeah, does anyone remember what an asymptote is? We should look at our last lesson, because it was there. A function that a graph or curve approaches.
So do we have to write our own function, or?
Nope, the function's already there. Y equals 0. Remember how the exponential was approaching the x-axis? And the equation for that x-axis was y equals 0? So what would the asymptote be for the inverse function? X equals 0.
We're so good.
Crushing it, right? It's now approaching the y-axis, right? Right here. And so that's the equation x equals 0. It's what that curve is approaching. So intervals of increase and decrease. What's the exponential function doing? Increase or decrease? Increase. And what is the interval of increase? I didn't know it was supposed to rain today. Bummer.
It's
supposed to rain like
for 3 hours. They both increasing, right?
It's only increasing, so what is the domain interval over which it's increasing? What's the lowest x where it starts to increase?
Oh wait, no.
For the exponential? Negative infinity. Because remember, we want the domain, the x values. The lowest domain value that starts increasing is all the way here at negative infinity. Where does it stop increasing?
Positive.
Positive, it's going to keep going. Okay? So look at that inverse function. What's the domain interval over what? Is it increasing or decreasing, first off? Increasing, right? Notice if I do a tangent line slope, or slope of that tangent line is what? So it's positive, that means it's increasing. So what is my interval of increase? So remember, the intervals of increase and decrease, are they domain or are they range values? Domain. So what is the lowest domain value that it starts to increase at? 0. Notice it never goes to the left of that 0, does it?
No, it don't go to the 0.
Right, so the lowest is 0, what's the max? Positive infinity. In behavior, now I'm going to need a little bit more room for this. So what type? How many in behaviors do we have?
4.
Sorry, just for f of x. 2. Because there is the left hand in behavior. And so I'm going to do f of x first up here. And then have the right hand in behavior. Left hand in behavior as
X approaches negative infinity.
Y is.
Y approaches positive.
Wait.
Oh,
so as x goes towards negative infinity, y is approaching positive.
oh, there.
Yeah.
Oh, no, one's approaching 0.
Remember, that's the whole point of a horizontal asymptote, is we're approaching it, right?
Why still going up?
Not over here, it's not. As I go to the left,
Oh.
see how it's going towards the x-axis, so is it y equals 0? Yeah. Right-hand in behavior, as x goes to the, so remember now I'm looking at the right-hand side,
If X goes to the right, positive,
which is
positive infinity, Y is going up to positive infinity.
going up to positive infinity. So let's look at this. Don't even look at the graph. Or the inverse of f of x. Left-hand in behavior. Don't look at the graph, just look what's right here. What would we guess?
Positive. Zero.
As x approaches what?
Positive.
Looking at this? What do we know about those inverses?
They're opposite of each other. So if you like.
Be careful with that language, not an opposite.
They're inverse.
They're inverses.
So if you like, if X approaches to the Is it X approaches zero?
As x approaches 0.
Right, it'll be zero, and y be extended.
Remember, what's going to happen to my x and y? They are going to switch, right? So instead of